Okay, now we're into Module 5B. Let me set this up for you, and then we're going to place some observations of pulsars. So in Module 5A, we began our study of star death. There are many different types of star death. So here we have a star-forming region. We studied these in Module 3. You produce stars, low-mass stars like our sun, and high-mass stars. And we studied stars and how they evolve in Module 2. Let's consider the low-mass stars first. They go through their life, become red giants, eventually produce a planetary nebula, throwing off the outer layers, leaving behind a white dwarf. We've already seen examples of this. Here's a picture of the Helix Nebula. This is just my LRGB layer tamped down. You can see that central star is bluer than the stars around it. That's the white dwarf. Here's another image. We saw this back when we were doing our star cluster observations. This is an open cluster. It just happens to have a totally unrelated planetary nebula. It's about 3 times closer to us than these background stars. And we see red, that's the H alpha. We see green, that's the O3. And this star in the middle is bluer than the stars around it. And that's the white dwarf. And it's fainter. Even though it's closer, it's fainter than the blue stars in the open cluster. And those white dwarfs are very faint because they're very small. They're about the size of the Earth. So there's not a lot of surface emission. They're hot, but there's not a lot of surface area to emit from. But you can see them in your optical images. But then you have high mass star formation and death. And as we learned before, high mass stars live hard and die young. They don't last long. So here it starts out blue, hot, massive, forms a red supergiant, and you get a supernova explosion. This is not like a planetary nebula where the layers just gently lift off. The thing collapses down, the core gets squished, and the most common output is a neutron star. So basically what happens in this case is the core gets squished so much, the protons and electrons are squeezed together and make a whole bunch of neutrons. And these regions are very small, about the size of a city. The rest of the star comes down, overcompresses that neutron core, bounces off violently, making a supernova explosion, leaving behind the neutron core as a neutron star. And if they're very massive, more than about 25 times the mass of the sun when they start, you can actually produce not a neutron star, but a black hole. Now, we're going to study black holes, or we did begin to study black holes in Module 4. Here, we're going to focus on the neutron stars. And we'll come back to black holes in Module 5C as well, and also in Module 7. We're going to see a lot of black holes, but here, we're going to focus on the neutron stars. So I said that neutron core is very small, about 10 kilometers in radius, 20 kilometers across, and it's very hot initially, but because of that small size, there's just no surface area. It's the surface area of Rhode Island. And so not a lot of light gets out. A lot of light per surface area, but there's hardly any surface area. So you don't really see these in your optical images. You can pick them out at other wavelengths, but you're not going to see them in your optical images. But sometimes you see them because they pulse. They have very strong magnetic fields, at least initially. Imagine taking the magnetic field of the sun, which is pretty normal, but squeezing it down the size of a city. That amplifies the magnetic field by the square of the radius. So it gets really, really, really strong. And as we learned previously, think of Jupiter's magnetic field. You get charges in a magnetic field, you're going to get synchrotron radiation. And we'll talk more about this later, but I'm just giving you some motivation before we place the observations. The other thing is it speeds up. As the star shrinks, contracts, it speeds up, much like a figure skater. you've seen this, the figure skater spinning around, pulls their arms in, and they go faster and faster and faster. There are also videos of astronauts doing the same thing, conservation of angular momentum. So this neutron star is spinning quickly. It's more massive than our sun. Even just the core of this star, it's like 1.4 times the mass of our sun, but maybe spinning once a second. And that's on the slow side. They can spin much faster under certain circumstances. And it has that magnetic field spitting out radiation. So combine the two, you have something like this. Now, most of the time, we're not along the line of sight of that pulse of synchrotron radiation, but sometimes we are. And it can be very bright, and can be very bright in the radio. So this is one of the activities where we're not going to make a picture. We're going to take a radio time series observation and study the pulsar from the pulsing. Okay.